are interested in the total cross-section, which as an example of the simplest things you can measure. If we take the total cross-section of E plus E minus into hadrons, normalize it to the total cross-section of the simple process, then, of course, the difference in the two calculations is just in the charge of the produced particles. So you get the sum over all particles with their charges. And the angular distribution, as we already mentioned, is expected to be 1 plus cosine theta squared, so this is there. Now, let's move to the next leading order. In the next leading order in QCD, what can we calculate? And this is not necessarily what we observed. What we can calculate is E plus E minus producing a pair of quarks and antiquarks, and then with the emission of the gluon. So a 2 to 3 process. This is what's called a tree diagram, which involving a real gluon emission. Now, with 3 particles, we have to talk a little bit about kinematics. As I also indicated earlier, a set of useful variable is the fraction of energy carried by each of these 3 particles divided by the full energy. So these are variables which go from 0 to 1. And energy conservation tells us that the sum of the 3 x's should come to 2. So only 2 of them are independent, which also means that if you use the scattering angle between the 2 and 3 and the 3 and 1 and so on, then these x variables and the theta variables are equivalent to each other. And the relations are like this. So again, this is a calculation that most of you should be able to do. And if you calculate the differential cross-section first, and then you integrate in order to get the total cross-section, normalize to the point-like thing, and then the result is actually quite simple. It's x1, oops, so it has to be x2, it should be x2, x1 squared, x2 squared divided by this. Or equivalently, you can write it in terms, as I said, about 1 and 3, 2 and 3, and it's all equivalent. Now, you say, what's wrong? This is totally finite and well-behaved and so on. Well, except, as you notice, of course, what if x1 goes close to 1, or x2 close to 1, or x3 close to 1, because you can rewrite this. All of those cases, you actually, this will diverge. When you try to get the total cross-section, by integrating this, you have to go near these points, and you will get into trouble, therefore. So here's that diagram again. And in the center of mass, you have these three momenta. This is the angle. And you can picture because the 3 variables are dependent, you can picture the kinematics by this triangle kind of structure, which is, some of you may have heard the name. This is called the Dalitz plot. When you organize x1 in this direction, x2, x3, then you can show that the allowed kinematic space is the inside of this triangle, and the sum of the 3 is automatically equal to 2 as it's constructed. And this is a well-known tool for analyzing 3 particle final states dating back to the 50s and 60s. In this plot, you can also show that, for instance, along this line, which this is x2 gets to be as large as it can be, then this forces x1 and the momenta 1 and 3 actually to be collinear. So this is a collinear configuration. This is a collinear configuration. This is a collinear configuration. And when you go near the vertices, this is x1 equal to 0, x2 equal to 0. So these are the so-called soft regions where the energy of one of the particles becomes equal to 0, close to 0, and the other two, of course, would then go back to back. So as indicated here. The thing is, this cross-section formula that you can calculate becomes divergent both when you go to the vertices, this is a soft, give you a soft divergence, and then if it goes to near the boundary here, you get collinear divergence. So given the fact that this simple calculation gives you divergent results, I mean, how are you going to deal with this problem? You can also show that in either of these configurations, this is when this propagator here, these are all real particles. Here is one virtual exchange particle. These configurations correspond to the fact that this k squared goes to 0, namely, since the propagator is 1 over k squared, so that is, of course, that's why it diverges. So one thing we learn from this is that singularities occur at the boundaries of the phase space. What characterizes both the sides and the vertices is that at those points where it becomes singular, the 2 particle to 3 particle kinematics actually collapses into a 2 to 2 kinematics, back to back. Always back to back. It's under those circumstances you get divergences. Now, for theorists, at least, this is when in the science of analyzing Feynman diagrams in general, these are places which corresponds to jargons now. Solutions to the Landau equations for pinch surfaces of the Feynman diagrams. No, I'm not going to explain what that means. Those of you who are interested in it should consult the Tasi lecture notes of Sturman of some mid-90s, and there's an extensive discussion of that. Now, we also like to gain a little bit understanding, a deeper understanding, by asking for those kind of kinematic configurations which I described in momentum space, what is the space-time picture which relates to this? Now, to discuss that, it is useful to introduce variables which are called no-plane coordinates or light cone coordinates sometimes. Namely, we have an E plus E minus interaction like this. You have an axis which of the colliding axis. And if you define the components as plus minus the energy and the momentum in the z direction from these combinations, and you get the so-called light cone components, then typically when you calculate these Feynman diagrams and you transform between the space-time variable and the momentum variable, you have to do a Fourier transform like this. The exponent of this then becomes x minus k plus x plus k minus, and then it transfers. And the mass shell condition, the k squared equal to 0, that's where the singularity occurs. On the mass shell, the minus component then is related to the other components like this. Okay? So when at very high energies, when let's say the energy becomes very large and the momentum along the third direction becomes large, then let's say if k plus becomes very large, then k minus would then be inversely proportional to that, goes to 0. And of course, because of complementarity, when you take the Fourier transform, that corresponds to k minus going to 0 means that k plus, x plus in this coordinate space becomes very large. So here's a picture. Here are your Cartesian coordinates, and here are the light cone coordinates. Here's a mass shell. And when k plus becomes very large, k minus becomes 0, so you are forced to be along here. In this space-time picture, when two particles come in and scatter, the x near the singularities, again, you take the Fourier transform here, the contributing values of x, as I already mentioned, which corresponds to k minus going to 0, is very large, x plus, and corresponds to very small x, small x minus. So in other words, we are here. X minus going in this direction has to be very small. X plus is large. So you are, this is then a typical space-time kind of a picture. What we learn from this simple discussion is that the singularities which are associated with the divergent perturbation calculation corresponds to a long time. That is because in the light cone description, this is equivalent of the time variable, and this corresponds to a long time after the creation of the initial interaction at the vertex. So, what do we do then with this long distance physics, which leads to these collinear or soft divergences? As I already mentioned in the last lecture, the first way to deal with that is to realize that there are physical variables which are insensitive to the long distance behavior of the theory. If it's insensitive to the long distance behavior, then it won't be bothered by these singularities you encounter. Or, in other words, as we'll see, these singularities will cancel, and leaving you with results which do make sense, which are finite, and make sense, which can be compared with experiments. So one example is this total cross-section. The total cross-section is obtained from the differential cross-section I just mentioned by integration. The statement here is that if we now integrate that expression over the entire phase space, even if naively for the particular diagram I showed you, we see singularities, but if you add up everything, actually those divergences go away. The reason is I discussed this diagram, but I have not included another diagram of this kind. This is E plus E minus going to quark anti-quark pair, but exchanging a gluon, a virtual gluon. So this is a real gluon, this is a virtual gluon. The interference term between this diagram and the Born diagram is of the same order as this diagram. So if you do a next leading order calculation of the total cross-section, you have to include the square of this plus the interference between the Born diagram with this diagram. You have to add the two results up in order to get the total cross-section. Lo and behold, when you do that, there is a cancellation of all exact cancellation between the divergence which we encountered earlier with the same divergence here, which occur with exactly the opposite sign. So, the physical reason for this cancellation is that actually, I'll mention this in the next slide also. The point is, the reason the total cross-section is insensitive to this long distance behavior is because if you calculate E plus E minus going to quark anti-quark scattering, just like you do for E plus E minus going to mu plus mu minus, let's say, at short distance, then once the pair is produced, then the probability of the fact that the quark and anti-quark pair will turn into some hadrons, since you are measuring the total cross-section, you don't care what hadron it produces. But once it's produced, the probability for producing any hadrons is unity. And that is independent of how it turns into a particular pair of strongly interacting particles. And those are sensitive to long distance. But if you sum over everything, it's independent of the long distance behavior. The usefulness of this infrared safe variables was first pointed out in a seminal paper by Sterman and Weinberg. And in addition to beyond the total cross-section, and they pointed out the usefulness of the jet cross-sections, which are infrared safe. And the modern variants of this, of course, are more familiar to most of you. Starting from E plus E minus days, there's the J definition of jets. In hadron colliders, the cone definitions, now KT definitions, and so on. Of course, we will have lectures on the jet physics, and we will talk more about that. Similarly, for the extensive work done on E plus E minus QCD studies, there are a whole range of so-called shape variables, which I will talk about thrust a little bit, but details will also be given in that E plus E minus. There are other infrared safe quantities, energy-energy correlations, and so on. But there are a long list, but they are not everything clearly. The basic idea, which the total cross-section was an example, if behind the infrared safety is precisely as we already indicated. Infrared safe quantities are typically those where, by the definition of that variable, the calculated result is insensitive to whether you are calculating the n particle final state or n plus 1 final state, as long as the n plus 1 final state is in a configuration which is reduced to a simpler, collapses into a simpler kinematics. That's where the singularities occur. But if this quantity you are defining is insensitive to that distinction, then that's when such quantities become infrared safe. So a more elaborate definition in terms of formulas is that if you want to define an infrared safe quantity, you have to be prepared to give a definition of a set of quantities Sn, n from 0 to infinity, such that it's a sum of all of these, but the necessary and sufficient condition is that for the n plus 1 definition, if you split the momentum up in this fashion, these two become either collinear or soft, depending on these conditions. Then the requirement is this reduced to that. And then if this is true, then you should have a quantity which is infrared safe and calculable. The simplest example, again, is the one total cross-section. In that case, you simply define all of these to be equal to 1. It clearly satisfies that criteria, right? If I split this momentum into two parts, it's still equal to 1. So there's no difference between Sn and Sn plus 1 when it's split up. The next one is the thrust, which is not the first shape parameter introduced, but it's now the most often used one. Its definition goes something like this, which I won't elaborate. As you can see, our time slips pretty fast. So this is the thrust parameter, which is defined in terms of a set of quantities like this, which in turn is defined as the projection of the produced particles dotted into a unit vector divided by its magnitude. So this is like a fractional, the magnitude, like a cosine angle kind of thing. And then you maximize this quantity by letting this unit vector to go in different directions. And this quantity is infrared safe. Well, this I'm sure will be talked about more in that lecture. This is obviously infrared safe because if when x goes to 0, when in the soft limit, one of the momenta just drop out. In the collinear limit, all these vectors are collinear. Therefore, this quantity, both the denominator and the numerator have these properties. Therefore, it stays the same. If this is not clear to you, just wait until you have your E plus E minus lecture. Now the next question is, are applications of predictive QCD confined to only infrared safe quantities where you can actually calculate? Well, fortunately not, because again, these variables are still relatively limited in number. So the QCD pattern model then comes from the next property, which is the factorization. The factorization does not does not get rid of the long distance physics completely, but this idea allows us to isolate the long distance physics from the short distance physics, and then you are saved by the fact that long distance physics part, which you cannot calculate, as I said, are universal. Therefore, they can be still treated phenomenologically, but then we can make lots of predictions based on the calculation we can do with the short distance part. In the context of E plus E minus, this occurs when you look at quantities such as one particle inclusive cross-section. E plus E minus scattering produces, instead of jets, let's say produces, you measure one of the outgoing particles, let's say a pion, and then you don't care about what happens to the rest. So it's a semi-inclusive in the sense that you do observe one of the particles, but you make it inclusive by summing over all the other particles. In pictorial form, the factorization works this way. It says that you have a short distance scattering near where the interaction vertex is, but then as time evolves, long distance physics actually comes in when this observed particle is observed, and so necessarily long distance physics comes in, because to produce a pion, the confinement part of QCD has to come into play in order to produce a pion. But the long distance part, however, for this inclusive process actually is universal. It can be summarized in this function, which is a fragmentation function in this case. And the short distance part, you can still calculate. And observed cross-section then becomes a convolution integral between the of this short distance part and long distance part. The separation is made at a particular scale, just like for renormalization. When I talk about when you introduce the idea of renormalization, ultraviolet renormalization, a renormalization scale necessarily have to be introduced. Here, a scale also has to be introduced. This is the so-called factorization scale. And it is usually chosen to be at the hard scale we are doing our experiment. And this then is the factorization theorem, which is which forms the pattern picture, the pattern language we use, but analytically it is the factorization theorem which has to be proved order by order imperturbation theory. I'm not going to prove this or talk about this until I get to the deep inelastic scattering part. But I just want to give you a preview of what it is like in the context of E plus E minus here. So assume that knowing that factorization forms the basis of the pattern picture, let's just go over all the processes which our considerations will apply, or which will be sort of cover most of the subjects of this summer school. We have E plus E minus annihilation, which I have already talked about, and there are many measurements of various physical quantities, through the last 20 years, starting from the lower energy machines through to the lab and so on, and ILC. When this slide was made, it was still the NLC, but now it's the ILC, I guess. So deep inelastic scattering falls into the category of lepton hadron scattering, and where the pattern picture looks like this. We use this all the time, and in this way, in these diagrams, the blue squares indicate short distance physics we can calculate. The green ones indicate the long distance, the universal pattern distributions and fragmentation functions. And then, of course, for hadron colliders, we can have standard model processes such as P bar or PP going into a WZ gamma or Dralian pair, or the bottom top Higgs and extra dimension particles, whatever. So clearly, this is to understand the underlying physics behind all of this is what we are going to do for the next 2.5 hours, I guess. So let me move to the next file, which is this one. Bring up the other one. How do I get rid of this? What? It's busy. Oh no, I know what's going to happen. This thing, did it reset itself again? No. Nope, alright. This is the resolution change. That's what I'm afraid. Okay, we're still okay. So we're now moving into the third part of the lecture, is on deep inelastic scattering. Again, now I will, because deep inelastic scattering is such an important process, I will spend a little bit time on the cross-sections and structure function definitions. And then the alpha 0, the leading order part, of course, still is a Poisson model. So we'll spend very little time on that. Again, most of the emphasis will be on the next leading order. I will emphasize the physics that I will discuss is similar to what I've discussed for E plus E minus. But as I also mentioned in my introduction, I will try to do this in a totally different way so that you can get a different perspective. We'll end up in the same place. Deep inelastic scattering, I'm sure you have seen this for many, many times. I'm going to go through this very quickly, partly just to bring everybody on the same page, but also hopefully I'll give you some slightly different perspective than what you normally see in the usual talk or in the usual paper. So we are talking about electron, neutrino, or muon coming in, scattering, and we're basically probing the hadron here using a vector boson. So we're going to use one vector boson exchange mechanism for the electroweak part of the interaction, and this is where all the action is. The familiar kinematic variable is the energy loss variable, E1 minus E2, and the Bjorken X, and a Y variable, which is mu divided by the incoming energy. The cross-section, of course, is given by this familiar formula, flux factor, matrix element squared, and integrating over all the final states. Now, when you are asked to write down such a matrix element, here is a structure. You have a lepton vertex, hadron vertex here, and here's your propagator, 1 over the propagator, and with because this is vector, there's a certain vector structure to that. The gauge coupling constant here, depending on whether you have the gamma or the W or Z, the unified electroweak theory give you the couplings. The lepton current part, this is calculable, right? So it's given by this expression with coupling, left-handed and right-handed coupling, chiral couplings. And similarly, if you have quarks, it's of the same structure here, although we are, of course, interested in hadrons, not in quarks and gluons. So here is just a list of the vector and axial vector coupling, or the right-handed, equivalently, the right-handed or left-handed coupling for gamma exchange, Z exchange, W exchange, depending on the electroweak isospin and charge. And these are all in textbooks. With quarks, in addition, you have the mixing matrix, the CTEM matrix. All are in textbooks, but I want to mention them so you know in the back of your mind what's involved in them. All right, the cross-section is given by the square of the matrix element, which I just mentioned. So typically, double differential cross-section is like this, with the square of the propagators, and then the square of the lepton part, the square of the hadron part, the lepton part again, so the square here. So it's calculable. Again, this is such a simple calculation that every one of you should have done it in your homework. And here they are. And the hadron part involves the matrix element between the proton and the final state, which you sum over, X is summed over, of the hadron current. So this involves the QCD dynamics. This involves the long-distance physics that we're talking about. So you cannot calculate this immediately, or not immediately, but we don't know how to calculate them from first principle. But you can, however, simplify this expression. Instead of a 4x4 matrix. General considerations allows you to rewrite this in terms of three invariant structure functions, usually called W1, W2, W3, historically. And the W1, W2, W3 embodies all the QCD physics. So, because the rest of them are calculable, to talk about QCD physics, we can just concentrate on these quantities, or this quantity in general, and that is illustrated by this picture here. So the leptonic part is factored out. So we're talking about, this is what summing over all final states by using the optical theorem. So we're dealing with the forward Compton amplitude, a virtual gamma or W or Z scattering on proton, forward scattering into the same final states. The cross-section can be written in various different ways. The structure function, so the cross-sections are then given by these irreducible structure functions, W1, W2, W3. But there are three different ways of writing this, or three sets of equivalent structure functions. Historically, it was first derived in this way in analogy to the Rosenbluth formula for elastic scattering in terms of lab energy and scattering angle. After the Patang picture was introduced, that the Biot-Kent scaling became an important concept, we introduced new structure functions. Nowadays, I call them scaling structure functions, F1, F2, F3, which to zeroth order approximation are functions of X only. Again, with general couplings, and it looked a little bit messy. And the third way of writing this is really my favorite way. I think has the most physically apparent interpretation, is the helicity structure functions. Written in terms of the helicity structure functions, again, in the most general case with general couplings, you have the longitudinal structure function multiplied by the sine of this scattering angle, if you like. This is a hyperbolic sine. And the transverse structure function multiplied by the familiar 1 plus cosine coefficients. And then, because you can have parity violation, this is the W3 part, which is, I call the parity violating structure function, which is just multiplied by cosine theta. So this formula looks very much like E plus E minus, or Drell-Yan, emphasizing the same underlying structure. And these functions all have scaling behavior, and that's why I like it so much. So just to remind you, these are the analogs of these factors for E plus E minus, for time-like vector bosons. The relation between this angle, hyperbolic angle, and the more familiar variable y is that the cosh of this becomes 2 minus y divided by y. All right. The relation between the scaling structure functions and the historical W1, W2, W3 is given here. As you can see, the W2 and W3 are not does not have scaling behavior as the way it came, but if you multiply by nu, they become scaling. The helicity structure functions it's physical in the sense that it's just this amplitude sandwiched between the polarization vectors of a helicity plus 1, minus 1, or 0 vector boson on the target. So it's very physical scattering amplitude. The relation between these invariant scaling F1, F2, F3 and the helicity ones, right-handed, left-handed, longitudinal, are very simple. There is this factor kappa here, which is effectively 1 because at very high energies, because Q squared is much smaller than mu squared. So if you forget about kappa, the relations are very simple. In fact, the F1, the usual F1, is just this transverse, which is right-handed plus left-handed. F3 is exactly equal to the parity violating one. F2 is a combination of the transverse and the longitudinal with a factor. Now, when you do a deep inelastic scattering experiment, what physics are we probing? I think since my time actually I'm much slower than my plan was, I will skip this part, and you will, those of you who are interested, can go through this, these slides and convince yourself again that let me see, what do I have a bottom line? Not really. So I won't waste time on this. So let me just move on to discuss deep inelastic scattering using the language that I have already introduced. The structure functions at the parton model level, say, imagine going back to 1970 when the SLAC experiments first became available, when Bjorken and Feynman introduced the ideas of the parton model. This is basically the picture they were talking about. That here's a proton, you do a scattering, then they say you can explain the scattering by interpreting the results as the probability of finding a parton, little a, inside the proton, and that parton is responsible for the hard scattering. And if you want to ask what's the prediction of this picture, then all what you do is to calculate this hard scattering part, which when you square this amplitude becomes this Born diagram for, so this is just that part here, you square this. When you do a simple calculation of this, which is very similar to the calculation for E plus E minus, we mentioned just turn it around, right? And the conclusion would then, in terms of the helicity structure functions, is simply that this is a hard scattering part inside here with a hat, indicates the hard scattering part. You will find when expressed in terms of this helicity structure functions, all what you find is that there's no parity violation for scattering of a virtual photon that we know. Longitudinal structure function equal to 0. That's the equivalent of the E plus E minus going into 1 plus cosine theta. And the only non-zero part is the transverse part, which is proportional to the charge of the parton. This is a totally identical to the results of E plus E minus at the leading order I mentioned. All right? And if you express, so that's repeated here. And the fact that at the parton level, the probability of finding a parton little a in the hadron A only depends on the fraction of energy carried by the parton, an idea introduced by Bjorken, means that this function, it is in principle a function of two variables, but for this hard scattering, for this kind of Rutherford, modern day Rutherford scattering, you expect it to be only a function of x, that's Bjorken scaling. And this result historically is the Kelvin-Gross relation, which is, as you learn the Kelvin-Gross relation, you probably learned it as something like F1 equal to 2x times F2 or something like that, which has no obvious physical interpretation, but in terms of helicity structure function, it simply says that quarks with spin and a half couples only longitudinally, only transversely, not longitudinally. So that, in terms of the F1 to 3, that's the result, and the F1 and F2 are related to each other, and that's the equivalent of this formula here. The helicity version, I think, should be obvious that it's simpler and it has a more immediate physical interpretation. Now, if you extend this to neutrino scattering, the results are even more remarkable. This will be left as a homework exercise again, right? And you should be able to do this. If you put in neutrinos and the antineutrinos couple according to the unified electroweak interaction, only to left-handed, the W mesons couple left-handedly to the quarks and anti-quarks, and they don't couple to the gluons. And here I indicate the results by using capital U to indicate a generic up quark, and capital D a generic down quark. So it could be a usual up quark and down quark, or a charm and the strange, or a bottom and a top and a bottom, and of course with the appropriate CKM mixing. You see the results are extremely simple again. Only the W's which couple to down quarks only is left-handed, and it coupled to the anti-quarks right-handedly, but only the, for instance, the anti-quark of the up kind couple. So right-handed structure functions are associated with anti-quarks. The left-handed structure functions are associated with the quarks, and for antineutrinos, it goes the other way. So, in fact, you don't need to do any complicated calculations. This is rule of thumb, give you all the results. Again, this is only happens when you use the helicity language. For neutrons, but that's all for protons. For neutrons, of course, all what you do is to interchange the U quark with the D quark and leave the charm and strange and so on alone. And then when you actually do neutrino scattering, most of the existing neutrino experiments are done with heavy targets. It's a mixture of protons and neutrons, and so if you, for isoscalar target, you have these combinations. So you just have to supplement the previous slide with these simple things, then you can get all sorts of simple parton expressions for measurable quantities, all in terms of these parton distribution functions. A particularly useful combination is the transverse structure function for neutrino, antineutrino scattering, a mixed neutrino-antineutrino beam on a nucleon target, where you add up all of these things. So that's just proportional to x times the parton distribution functions of all the quarks and anti-quarks. And that's very useful because that gives you the total momentum fraction carried by all the quarks and anti-quarks. And if you believe in momentum conservation, 1 minus this quantity is exactly the momentum fraction carried by the gluon. And that actually is a very useful relation. From this, you can derive some rules. For instance, all kinds of sum rules which goes by the name of Bjorken sum rule, Adler sum rules, Llewellyn-Smith, these were all derived from theoretical considerations through a long series of arguments and so on. But all those very lengthy arguments becomes simplified and becomes sort of particular cases or combinations of simple Parton model results, such as these, which have obviously obvious interpretations. For instance, U minus U bar, that's the valence quark inside the proton. And of course, you integrate over all the momentum fraction, you get two U quarks inside the proton, one D quark, down quark inside the proton, no net strange quark inside the proton. These are the quark number sum rules. And you can form all kinds of combinations, which, as I said, will lead you to the many of the historical sum rules, which I won't list them for you. And then the momentum sum rule, which says the sum over the gluon momentum fraction and all the quark and quarks should be equal to 1 here, which is missing. These are all in the context of the simple Parton model. One interesting thing about QCD is that after we turn on the QCD interaction, very complicated dynamics, all the quantum field theory complications come in. But after everything is said and done, after you've proven the factorization theorem and so on, you can also show that this sum rule remains true in QCD. Here I have functions of x only. When QCD is turned on, these actually have Q dependence. But you can show that when you form these particular combinations, then the net result actually would be independent of Q squared. So those are all quite profound results. All right. So let's then this summarizes what I already said. So let's move ahead. Now let's discuss these structure functions beyond the Parton model. At leading order, we produce the Parton model, so I skip this. So for the rest of my lectures, I will go through the next leading order discussion as much as I can. Clearly, as you can see, with the time available, I cannot go into too much details, but I do want to give you a feeling about when you solve the quantum field theory, why the features I mentioned will emerge. So I think I have 5 more minutes for this lecture, so I'll give you a start, and then tomorrow we'll go through the more details. Okay? So what do we get ourselves into when we go to next leading order? And next leading order, 2 Feynman diagrams come in. You scatter this virtual photon, let's say, on a gluon, producing a pair anti-gluon pair, or you scatter this on a quark and emits a gluon in the final state. This diagram is, again, similar to the diagram we talked about for E plus E minus. Just pull some of the legs, the 3 particle final states, pull one of the legs over, and you get this. So again, this is a calculation. I'm sure this is a calculation you have done if you've ever taken a course in advanced quantum mechanics or first course in quantum field theory. So the result I will quote should be familiar. These 2 processes do not interfere because they involve different final states. So I have the square of this amplitude, the square of this amplitude. So because of that simplification, I will leave this out completely. I will only discuss this because this is simpler. We have no time really to go into the details here, although I will mention what difference does it make in the end. This calculation is particularly simple, and I think it will give you all the physics, basic idea of the physics that I like to illustrate. So that's what I'm going to concentrate on. So what's the calculation? You square that amplitude. So that means is that you calculate this forward Compton amplitude with these two particle exchange. So these are the two terms you need. For this calculation, I will keep the quark mass to be non-zero. This is done for several reasons. One of which is that then the result is finite. I do not see any divergence. So the collinear and soft divergence that I mentioned earlier will manifest itself in a slightly different form, give you a different perspective, and show you exactly why it's called collinear. And another reason for keeping the mass is because this actually has something to do later on with heavy quark physics, which I won't have time to talk about. And in the heavy quark course, I think it will re-emerge again. The point I'd like to emphasize there is that the factorization theorem that we ended up with, if you read it up in the textbook, it's always proven with zero mass quarks. Any proof that you see in textbooks, first set the mass equal to zero, then prove the factorization theorem, giving you the impression that the mass, setting the mass equal to zero is a crucial ingredient of the factorization theorem. In fact, that's not true. And at the end of our discussion, you will see that when we demonstrate factorization, in the end, the idea which goes into it has nothing to do with the quark mass. So the factorization theorem actually is still true if you keep the mass. That's something that took a number of years to evolve. Many people know this implicitly, but the formal proof of this only happened in 1997, 98 or so, when John Collins showed that the full, complete proof of factorization doesn't depend on the mass at all. So this simple example will kind of underlies that fact. So this calculation is exactly the same one that you must have encountered in your course in advanced quantum mechanics. Therefore, I'm not going to do it for you, and you should know it. This is the result here. So this is the kinematics when you calculate this. And in the center of mass, again, you have these four components. And this is the result. In this result, there is this quantity called L, which involves a logarithm of your center of mass energy, which is related to Q squared, and the mass, which I have kept. The important, so I will stop in 1 or 2 minutes, just to, in fact, I would advise you from now until the next lecture tomorrow to actually take a look at this so we can go more smoothly tomorrow. I'm not going to discuss the details here, but the key of the physics, all the physics besides, which I will focus on, is on this logarithm factor. The logarithm factor is just the ratio, basically, of the hard scale Q, which is same as square root of S, divided by M. And the rest of the details doesn't matter very much. The physics involves, why do these factors arise? How are these factors related to the collinear singularities that we talked about? And how do we learn to handle these singularities? The reason this is a singularity is because when square root of S becomes very, very large, this logarithm becomes very, very large, and you seem to get a very large, divergent. This is where a divergent answer will come when you go to the the very high energy limit of Q goes to infinity. So we have to learn to deal with this. So the question is, how do you deal with this? Which part of the calculation is sensitive to this logarithm factor, which is not? And why do these factors factorize? Instead of cancel, we are talking about factorization now. So we want to show how does factors of this kind, A is universal, B that it naturally factorizes itself out so that it's harmless. Let me just stop here. Then, because there are lots to cover, if you come prepared by looking ahead a few transparencies, then the next lecture will go a little bit faster. All right.